So what, again, I want to take you through is a bunch of different things that we just don't necessarily visualize easily to kind of help with a bunch of these concepts. The first one is the fact, this will also be tied into next week's ones, but that electromagnetic radiation is a form of energy, therefore it's related to temperature and can generate heat. We've all heard of heat vision and infrared, and you've all used a microwave oven to generate heat. The biggest thing about turning radiation into heat is that it has to have the right wavelength to interact with whatever it is that's trying to heat up, right? Because for me to get hotter means I get a higher energy. So photons or radiation or electromagnetic waves, whatever you want to call them, if it doesn't interact with something, it won't heat it up. So light, what does light do with glass? Does it really heat it up? I mean, it can, but the actual, if I had just visible light, what do you think it does? Like when you look at a piece of glass, can you see through it? Yes. Yeah. So what's the visible light doing? Passing through. That's how you can see through it. So the visible light doesn't heat it up much. However, other wavelengths, like infrared and microwave, get absorbed. You can't see them to begin with, so you don't see them getting absorbed. But they get absorbed, and that warms up the glass. Likewise, a microwave oven works literally because the microwave radiation is ideal for being absorbed by water. So it takes that energy, turns it into kinetic energy, and since temperature measures energy, your food gets hotter. So what we're going to do, I should have turned that on to start with, but we basically have a coil here that I'm running an oscillating current through, and it's going to heat up. And that heat will send off radiation. In this case, it's glowing red, so it is sending off some visible light. But it's also sending off the infrared radiation that you can't see. That's being focused by the mirror. The silver mirror still reflects it. It's a parabolic. Actually, I don't know whether this is parabolic or spherical. But it basically is focusing it, and it's focusing down to where this match is. And if you put your hand in here, you would see that it's getting quite hot. Now, hopefully the match is located well, and it will eventually burst into flame. Hopefully now you can see the smoke. And if you look closely, I mean, you can also smell the smoke. You can see the match starting to reflect a little bit of the red, and it'll get brown. If you want to like convince yourself it's getting hot, you can come and just kind of put your finger right there if you want to. It did? We have independent confirmation, and he's not a plant in the audience. I didn't pay him to say it was hot. So now we notice it bursting into flame. Very exciting. The next thing I want to do, so that's radiation going into temperature and transferring energy. The other way we can transfer energy is mechanically. So what I have here is a whole bag. Inside is lead shot. And so if I look at it, the temperature is about 20.5 degrees now. Okay? 20.6 maybe. And one way we can make energy, we said, is mechanical and through forces. So what I can do is I can take this and drop it. 2, 3. This is my workout for the day. 4.
What's in there?
Lead shot. So 5, 6. We're using something that's got a very low conductivity so that the energy I'm putting in doesn't leave easily. Oh, I broke it. 8, 9, 10. Okay, now oops. Probably breathing lead all day today. That's going to be great. Okay, now notice we're already up. Just dropping it 10 times, I basically went up almost a degree. 21.4, 21.5. Okay? And so you can see it's very repeatable. Why? Because I'm putting the same amount of energy in each time. I'm dropping it from however high my hand is, and I'm dropping it 10 times. That's 10 times mgh worth of energy. it has a certain specific heat, and that tells us how much the temperature will change for a given change in energy. And that's what we got. So again, hard to visualize, but this was actually one of the key first experiments that was done pretty much, I think, in the 1800s, where they figured out that mechanical energy and heat were the same. Actually did it by paddling in water, by putting paddles in water, spinning around and heating up the water. Now the other set of experiments have to do, again, with heat conduction. And there's a couple of different things to do. Try and get, again, at some of these material properties that heat causes that are a little harder to see at times. So there is our heat source. One of the first things, we didn't really put it on our list, but when you heat and cool things, what happens to their density? Does the density change? Yeah. Does the material do what? The density changes because the material expands and contracts. So if I heat it, it tends to what? Expand. Okay. One of the things that's very interesting, water is one of the strangest materials. Does anyone know where its lowest density is? Yeah, it's actually lowest density is a little bit as ice. Well, it's not its lowest density. Its highest density, I should have asked, is the water at a temperature just before we get it turned into ice. And that's why ice floats. Right? If you think about it, it's kind of weird. Ice is a solid that floats on the liquid it's made out of. That usually doesn't happen. And that's one of the reasons that life actually happens. But if I have two solids, in this case it's steel and brass, their thermal expansions, as we call it, are going to be different. So if I put them next to each other and I heat it, they're going to kind of try and stretch by different amounts. And so the net effect is that it bends and curves. So why might this be a useful technological idea? Well, yeah, understanding how when you make stuff, what its properties are going to be. But what's a very simple application? When would you want a piece of metal to bend because of a change in temperature, do you think? Suppose you wanted something to not overheat, and it was run on electricity, and it started to get too hot, and you had a metal piece in it at the right place. What could you have it do? Well, you wouldn't even necessarily notify. You could just have it turn off, right? If this is required for the circuit to be connected, and if the temperature gets high enough that it bends enough, the circuit's now broken and it turns off. Or if you just have an air conditioner that you want turning on and off at a certain temperature, you could make a metallic switch in it. So you could make a temperature-based switch for your electric circuit by having the right two materials. And so there's other things you can do as well, but that's one of them. Now, so this is a ball, metal ball of a certain size. It goes through that hole. It doesn't go through this hole. If we said it heats when I expand it, how many of you think expanding these will make the hole bigger? Okay. How many think expanding it will make the hole smaller as it expands? Okay, 3 people raise their hand. How many people have no idea what I'm asking or don't want to guess? Okay, so we have a few thinking the hole gets bigger, a few thinking it gets smaller. Let's see what actually happens. So if I heat it, now the ball passes through. Why did the hole get bigger, for those who thought it got bigger?
Didn't we just explain that metal expands?
The metal expands, so why doesn't it expand into the hole as well?
Because why would it expand this way when it expands?
Basically, exactly. Think about it as if there was metal in the actual hole itself. All the metal moves out, including the metal in the hole. So just because there's no metal there doesn't mean it's not effectively moving out. Everything moves away from everything. And despite how it might look like everything moving away from everything means this stuff also moves into the middle, that's not true. The inner ring has to have all the molecules move away from each other. The only way to have that happen is for the inner ring to get bigger. That's the only way to actually move away. Okay. Make sense? Now we're going to do our thermoconductivity demo. What brave person would like to have a contest? Okay. Would you like copper or stainless steel to stick into the flame?
I'm scared now.
You want stainless steel? Okay. He wants stainless steel. Okay. We're going to stick it. Go ahead and stick it in the flame with me. And the basic idea is we're going to see who can hold it in the flame longer or who gets to feel the heat first. What idea do you think we're trying to get at here?
Which metal heats faster?
Which metal heats faster? So the speed at which we heat has to do with what? Which concept? Conductivity. Just offhand, does anyone know which has a better conductivity, copper or stainless steel? Copper. So most likely, unless he's a real wimp, I'm going to let go first. Is it feeling at all warm? Now, does that surprise you a little? I mean, you've just stuck a metal object into a hot flame, right?
It did surprise me.
Yeah, you would expect it to feel hot sooner.
Yeah.
But notice even the copper, which has a pretty high conductivity, because it's a sufficiently long rod and sufficiently massive, mine's starting to get warm now. Not so warm that I would have to let go, but warm enough that I can feel it. How's yours doing?
It's fine.
Yeah. So mine is definitely getting warmer. I could certainly hold it longer, but I certainly don't want to burn my hand. So I'm going to put mine down now. And yours, I assume, is still fine.
Yeah.
Yeah, just don't touch the end that was in the flame. So the end that was in the flame got hot, but it really didn't at all. So it really is, conductivity really does matter, and that really is kind of the key idea. Okay? So we've had the thermal conductivity, we've had the thermal expansion, we've had the differential thermal expansion. We had the successful lighting of the flame, which was exciting to see the flame burst into fire. I mean, the match burst into flame. We had using the mechanical energy to change the temperature. Now, the last bit I want to do, okay, is, I'll put a little bit more in so you can see it, is, again, get an idea from some of these by using liquid nitrogen. So that's liquid nitrogen. You can see the liquid, it's flowing. If you've never done it before, you might want to just quickly put your hand over the smoke and get its temperature to decide is that hot smoke or cold smoke. So the smoke was not hot. You know, and the common question I ask people is, why was the smoke not hot? We're used to smoke being hot. What do you think is the boiling point of liquid nitrogen?
Very low.
Very low. It's below 0 degrees centigrade. Okay? So we're below its boiling point. So it is hot enough now that this is actually boiling. And if you looked in there, you would see it's constantly bubbling. It would look like water on the stove at 100 degrees centigrade. Okay? So it is boiling. That's what it's doing. And so it's making steam. Well, technically steam is usually water vapor, but it's making the gas version of liquid nitrogen, which is gas nitrogen. And so you see it as steam, but it's cold steam. Now, what's most of the air in this balloon? Actually, no, I blew it up. You didn't see me blow it up, but I blew it up. Yeah, it's actually nitrogen. Most of the air is nitrogen. So my liquid nitrogen is at a temperature that the nitrogen in here would like to go liquid. So if I put the two things in contact, the stuff in the balloon is going to get cold. Notice that liquid nitrogen got momentarily hotter, so we got a burst of steam. Okay? And what's going to happen as the nitrogen in the balloon gets colder? It contracts, right? Because it slows down, lower energy, and it eventually turns into liquid when it gets cold enough. And the liquid takes up a lot less volume than the gas. And unfortunately, I don't have the right things to completely submerge it in, but I can get it pretty darn close. And when I take it out, it was a very tiny balloon. And now as it warms up, and you can even see the liquid along the side a little bit, it's going to turn back into a gas, and it's going to re-expand. Sometimes the rubber of the balloon does break or crack, and you don't get it fully expanding. But basically, we liquefied the gas by cooling it. That's what cooling does. Okay, you don't often see gas condensing. You usually see it going the other way. Most of the time you boil stuff, or you see ice freezing, water freezing, and melting. The gas one's harder to see. And so this is a time I can turn a gas into the liquid, and you can see it shrink. So it's kind of a cool thing to visualize that you don't get to see often.